Okay, so in this video we will learn about Rolle's theorem. So we will look at what the theorem says, then you take some few examples to help us understand the theorem. So the theorem says that suppose f is a continuous function on the closed interval ab and then differentiable in the open interval ab such that f of a equals what f of b. Then there is at least one point c which is in the open interval h which is in the open interval ab such that the derivative of the function at that point will be equal to what? 0. So this is what Rolle's theorem says. So first of all, the function has to be what? Continuous in the closed interval ab. So first of all, the function has to be continuous in the closed interval ab. And then also it has to be what? Differentiable at every single point in the open interval ab. And lastly, f of a should be equal to what? F of b. Okay, so let's say that what if all these conditions what are satisfied. Okay, if all these conditions here are satisfied, then there should be at least a single point c which is an element of the open interval ab. Okay, such that the derivative of the function at that point c will be equal to what? 0. That's what Rolle's theorem means. Okay, so now for a better understanding, let's use a graphical representation to explain this. Okay, so I'm going to use a graphical representation to explain what Rolle's theorem means. Okay, so I have this here. Okay, so let's say I have the graph of the function to be something like this. Okay, so this is the graph of the function. So here will be my point A, and then here is also my point B. So I have this side to be f of b, and then this side here to be what? F of what? A. Alright, so let's see that what the function has to be what? Continuous within this interval AB. Okay, so first the function has to be continuous in the interval AB. Okay, and then looking at this graph here, you don't have any jump in it. Okay, we don't have any jump in it. The graph is continuous everywhere. Okay, so you see that the first condition has been satisfied. So let's look at the second one. The function has to be what? Differentiable at every single point in the open interval AB. So that means that considering the function, okay, so when you take any number between this interval here, you should be able to what? Find the slope for that number. Okay, so when you take any number between this interval here, so you should be able to what? Find the slope for that number. Okay, so looking at this here, we don't have any discontinuity in it, and then we don't have any corners in it. If you have corners on a function, the function will not be differentiable at what? That corner. And looking at this, you don't have a corner in this, so we see the function is what? Continuous everywhere also. And then the last condition is that f of a should be equal to f of b. Okay, so that means that the corresponding y value of a should be equal to what? The y value of what? B. So looking at this graph here, if I'm to trace draw a straight line here, you see that what? F of a equals what? F of b. So this condition has also been satisfied. So Rolle's theorem says that what? If all these conditions are satisfied, then there will be a point C which is in the open interval what? AB. So there will be a point C which will be in the open interval AB such that what? The derivative of the function or the slope of the function at that point will be equal to what? 0. So looking at this graph here, Okay, looking at this graph here, if I'm to trace point C from here, okay, if I'm to trace point C from here, let's see, here is my C. If I'm to draw a tangent line at this point, okay, on the function, you see I have something like this, a horizontal line. Okay, so this horizontal line tells us that what the slope of the function is what is 0 over there. So when you trace this point to the x-axis here, you get our C here, and then our C must be between what the open interval a and then b. A and b, okay, a and b sometimes can be differentiable. Okay, they can be differentiable, but our main focus here is on the value between what a and b. So sometimes when you put the value of a in the slope of the function, you get an answer for it. Okay, same as the b, but our main focus is on the value between what a and b. So with this understanding, let's go ahead and then try some examples. Okay, so the first example I have here is f of x equals x to the power 2 plus 1. Okay, and then you are giving the interval to be -1 to 1. Okay, so let's prove whether what Rolle's theorem holds for what this function here. So for Rolle's theorem to hold for this function, first of all, the function has to be what continuous in the given interval -1 to 1, and then it has to be differentiable on the open interval -1 to 1, and also f of what -1 must be equal to what f of what 1. So if all these conditions hold, then you can go ahead and then find the value of what c. Okay, you can find the value of what c. Okay, so now let's check if the conditions here what are satisfied by this function here. Okay, so first of all, the function has to be what continuous in this closed interval. So how are you going to know that? So generally we know that what this is a polynomial function. Okay, and polynomial functions are continuous and then differentiable at every single point. Okay, so polynomial functions are continuous and then differentiable at every single point. So that tells us that these two conditions has been satisfied. Okay, so the next condition that we look at is what f of -1 should be equal to what f of 1. So f of -1 should be equal to what f of 1. So I'm going to put this -1 and then 1 in this function and see if we get the same values for these two. So I'll test for f of what -1. So let's see what we get for that. So that will be -1 to the power 2 plus 1. This will give me 1 plus 1, which will be equal to 2. So now let's test for f of 1. So for f of 1, I have what 1 squared plus 1. This will also give me 1 plus 1, which is also equals 2. So therefore we know that what f of what -1 equals what f of 1, and this equals what 2. So the third condition also holds. So if the third condition also holds, then let's find what our point C. So let's find our point C. Okay, so let's try and see that what at point C, the derivative of the function will be equal to what 0. So at point C, the derivative or the slope of the function will be equal to what 0. So now let's find the expression for the slope of what this function here. So that will be the first derivative of this function. That will be what f prime of x will be equal to what the derivative of x squared will be what 2x, and then the derivative of 1 will be what 0. So that's plus 0. So at the end I'll have my f prime to be equal to what 2x. Okay, so Rolle's theorem says that what there is as at least a single point C where the derivative of the function will be equal to what? 0, or where the slope of the function will be equal to what? 0. So that point is what? Point C. And this is the expression for what? The slope of what? The function. Okay. So Rolle's theorem says that there is a point C here which will make this expression what? Equal, which will make this expression what? 0, or which will make the slope what? 0. So if that's the case, when we put our C value here, the slope should be what? 0. So we have f prime of C to be equal to what? 2C, and this should give us what? 0. Okay, so when you now have this, we have to find for what? C, so that you know the value that will make the slope of the function equal to what? 0. So I have f prime of C to be equal to 2C, and this should be equal to what? 0. So I divide both sides by 2, I divide both sides by 2. So at the end I have my C to be equal to what? 0. So what that means is that at this point C here, the slope of what? The function was will be 0, telling us that what? At a point C in this open interval here, the slope of the function what? Will be horizontal, since it will be 0. So one thing you should look out for is that after you have found for your point C, okay, you should check whether it is what? In this open interval. Okay, you should check whether the point C is in this open interval. And when looking at this, of course, between -1 and 1, we get 0 there. So our point C is in this open interval. So therefore, Rolle's theorem is true for what? This function here. So let's take some few more examples. Okay, so I'll go ahead and write down the next question on the board. Okay, so we've been given the function f of x equals sine of x. Okay, on the interval 0 to 2 pi. 0 to 2 pi. Okay, so this is the function you've been given, so you should verify whether Rolle's theorem holds for this function. So what are the conditions? So the condition will be that, first of all, the function should be continuous between this closed interval. Okay, and then it should be what? Differentiable at every point in this open interval. And then also, okay, let me put the values there. Should be differentiable in the open interval 0 to 2 pi. And then also f of 0 should be equal to what? F of what? 2 pi. So if all these three conditions hold, then you can go ahead and then find for what? Our C value. Okay, so let's check. So is this function continuous within this interval 0 to 2 pi? Is it continuous in this interval? So looking at this is a trig function sine. Okay, you know the trig function sine and cosine are what? Continuous and then differentiable at every single point. Okay, so sine and cosine are continuous and then differentiable at every point, same as the polynomial function. So these two conditions has been what? Satisfied. So now let's test for the third condition, saying that what? F of 0 should be what? Equal to what? F of 2 pi. So let's test for that. So I'll first test for f of 0. So f of 0 will be equal to what? Sine of 0. Okay, and this should give me 0. And then f of 2 pi should be equal to sine of 2 pi. And then this should also be equal to what? 0. So therefore, you can see that what? F of 0 equals f of what? 2 pi. And then all this equals what? 0. So the third condition has also been what? Been satisfied. So if that's the case, then let's find what? Our point C. So at point C, the slope of the function will be equal to what? 0. So before you can find our point C, let's find what? The expression for what? The slope of what? This function. So let's find the first derivative of what? This function here. the first derivative of sine will be what? Cosine of what? X. So at point C, this slope here, okay, the slope of the function will be equal to 0. So that means when we put C here in the slope of the function, you should get an answer of what? 0. Okay, we should get an answer of 0. So if I want to find C, C will be equal to the cos inverse of what? 0. And this will give me pi on 2, which is the same as what? 90. Alright, so I have point to be what? I have my C point to be what? Pi on 2. Okay, so looking at this, it's not the time that the C values here what will be just a single value. Okay, sometimes you can have two or more C values here where the slope of the function will be equal to 0. But currently we have what? A single point here from our solution. But you know it's not only pi on 2 that when putting cosine of what? This when putting this function will give you 0. When I put 3 pi on 2 here, I'll get 0. Okay, when I put 5 over 2 pi here, I'll still get 0. Okay, so now for us to be able to get the other point, let's draw the graph of what? This function. And you know the function is what? It's a sine function, so the graph will just be what you normally call the sine wave. Okay, so the graph will be something like this. So let's draw the graph of a sine wave. So it will be something like this, then something like this, then something like this, continuously. So we've been given the interval from what? 0 to what? 2 pi. So here will be my 0, and then here will be my 2 pi. Okay, and then this side is what? Pi. Okay, so you see that when you trace a point here, and then when you trace a point here, same as this side also. Okay, you see that what the slope of the function at this point are 0 because they are horizontal. Okay, so I have one horizontal slope here, another horizontal slope here, and then another horizontal slope here. So you see that what you are getting more than what? A single point. So here will be what? Pi on 2. So here will be pi on 2, and then here will be what? 3 over 2 pi, and then this side will be 5 over 2 pi. Okay, so when we put 3 over 2 pi in this expression, cosine of what? X, we get what? 0. Same as pi on 2, same as what? This 3 over 2 pi, we get 0 for this. But you're not going to include any other value that comes afterwards 2 pi. Why? Because you've been given this interval from 0 to 2 pi. So it should be what? Only the value between this interval that will cause the function what to be, that will cause the slope of the function to be 0. So at the end you will see that we have pi on 2, and then 3 over 2 pi. Okay, so when we put these two values in this expression here, we'll get what? 0. So the next thing we have to verify is that these two values here has to be in this open interval. Okay, it has to be in this open interval. Now of course from 0 to 2 pi you have pi on 2 in it, and then we have what? 3 over 2 pi also in it. So these are the values that we are looking for. So this will be the C values for this function. So you will see that what Rolle's theorem therefore holds for what? This function also. So let's take another question. Okay, so now let's look at this example also. So here I have f of x to be equal to x to the power 4 minus 2 minus 2x squared minus 2x squared. Okay, on the given interval minus 2 to 2. So let's find out if Rolle's theorem holds for this expression also. So now let's write down the conditions. So the conditions are the function should be what continuous in this interval, and then it should be differentiable in the open interval -2 to 2. Okay. Then also f of what -2 should be equal to what f of what 2. If all these three conditions hold, then there will be a point C such that the slope of the function at that point will be equal to what? 0. Okay, so let's look at this. So now we are going to check if the condition is what the conditions what are true for this function. So first of all, we have to know whether this what continuous and then differentiable. So looking at this is a polynomial function. Okay, and you know polynomial functions are functions that has what a non-zero, sorry, that has what a non-negative exponent. Okay, so polynomial functions are functions that has what a non-negative exponent, and this is one of it. So you know that what polynomial functions what are continuous and differentiable what at every point. So these two conditions have been satisfied. So the next thing you have to look for is that f of -2 should be equal to what? F of 2. So let's check if that is also true for this function. So f of -2, okay, I'll have -2 to the power 4. Okay, -2 into brackets, -2 to the power 2. So this will give me 16, and then -2 square will give me -4. Okay, so -2 square will give me 4. Okay, times -2, this will give me -8. So when I subtract my 8 from 16, I have what? 8. So that's what you got for f of -2. So let's do same for f of 2. So for f of 2, I'll have 2 to the power 4 minus 2 into brackets what? 2 to the power 2. This will give me 16. 2 squared will be 4. 4 times -2 will be what? -8. So this also gives me what? 8. So therefore, this condition has also been satisfied since what? F of -2 equals what? F of 2. So if that's the case, then let's find what? Our point what? C, such that the slope of the function at that point will be equal to what? 0. So for us to be able to find the point C, let's find the expression for the slope of the function. So that will be the first derivative of what this function here. So that will be what f prime of x, okay, will be equal to the derivative of x to the power 4 will be what 4x to the power 3, and then the derivative of what x squared will be what 2x times what -2. So I'll get what -4x. Okay, so there is at least a single point C. Okay, so that what the derivative of the function there will be what equal to what 0. So I'll put my C here in this function here, then I'll equate it to what to 0. So now I have to what solve for what C. So now I have to solve for C. Okay, so let me write this here. So f prime of C should be equal to 4c cube minus what 4c, then this should be equal to what 0. Okay, so let me clear this off. Right, so now we want to find the values of what C. That will make the slope of the function what 0. So looking at here, I have 4c common to both sides. So I have 4c here, and from here also I get 4c there. So let me factor out 4c. So I have 4c. Okay, and then when you divide 4c to the power 3 by 4c, you have what c squared. Then when you divide 4c by 4c, you have what 1. So you have -1 here. Okay, so this should be equal to what 0. Now looking at what you have in the bracket here, okay, looking at what you have here, you see that what you have difference of what 2 squares here. So I have this to be equal to what 4c into bracket was c plus 1, and then c minus what 1, which is equal to what 0. Okay, so after doing this, I'm going to equate all the factors here to 0 so that what I find the value for what c. So first of all, I have what 4c to be equal to what, 0. So this will give me c to be 0. And then I have what c plus 1 to be equal to what 0. And this will give me c to be equal to what minus 1. And then the last part, I have c minus 1 to be equal to what 0. So I have what c to be equal to what 1. So these are the values of c that we have. So we have 0, minus 1, and then 1. So the next thing we have to look out for is that you check whether what these values here what are in this open interval. And you see between minus 2 and 2, you get 0 there, you get minus 1 there, and then you get 1 here also there. So that tells us that the function here also satisfies what Rolle's theorem.